Hello and welcome to Analyzer Shorts, the series where we show you bits and pieces about AnalyzerPro that should help and inspire you in your daily work as an expert. Today we're going to talk about the topic of pedestrian and cyclist accidents, specifically with a special method to deal with these cases, which is called the barrier method. All you need for that method is a final position of the car and the pedestrian or the cyclist. It's not so important to have the bicycle or the final position of the bicycle, but the cyclist itself and the car is important. We do not need a precise collision position. That's something we will find out in the process. Okay, I'm opening the module and I have already set up vehicles in the vehicle data. So vehicle number 1 is our pedestrian or the rider of the bike, number 2 is a car, BMW, and number 3 is a bicycle. So I've got to set it up. Our vehicle is number 2, person is number 1, and bicycle is number 3. Next thing we got to do is we have to set the final position of the vehicle. Then we have to give an area where the collision potentially could have happened. So we have pretty good traces, that is somewhere around in this area. We need to put in the final position of the person. And a final position of the bicycle. Furthermore, we could enter a splinter field for additional limitations, but in this case we don't have precise information about that. Next thing is and that's the main calculation step, we need to put in first of all a deceleration of the car, an average deceleration. So I'm saying maybe 7 plus minus 2 meters per square second. And then we have to select a theory. So all these different theories are for different settings. For example, if the car was braking before the accident or not. If it is for smaller people like kids or grown-ups. Or in that case, if it is like if we have to deal with a bicycle accident. You can look up all the detailed descriptions of all the different theories in our technical manual. So I'm selecting now the throwing distance for cyclists. And once I do that, you can immediately see that we see 4 curves or 2 pairs of curves together in that preview window. We have one upper and lower deceleration curve. It's because we have 7 plus minus 2, so one is for 9, one is for 6. And we have a second curve that comes from the theory. And how that is done is that there are crash tests with crash dummies under certain conditions, and these lead to potential landing spots for pedestrians or the rider of the bicycle in this case. And with that you get these resulting curves. And if you're now comparing the resulting curve with the deceleration curve and the limits of our collision location, then we get an overlapping area which is highlighted here in green, and that's our area of possible solution. I'm reducing this now to 7 plus minus 1, and we can see, okay, the area is getting even smaller. And now we see, or now we get a collision speed between 68 and 87 kilometers per hour as a result. In the extra barriers, we could deal with the splinter fields, but we don't have that here. So we can do another control calculation just with a throwing and sliding calculation for the person. I can select here, would I like to go with the minimum, medium or maximum version in terms of collision location, going for the medium one. Then a throwing off angle, which is typically very low in this case, so something like 5 degrees. Height difference if the center of gravity, so the center of gravity of a person is usually around its belly button, and first the person is on the bike, then it's lying on the ground, so we have something like -1 meter around that. And a sliding deceleration of a person on the ground, which is usually pretty high, so I'm going for 9 meters per square second here. And as a result, we get a takeoff speed, a throwing distance, of course the rest of that distance is then sliding on the ground, a maximal throwing height of the center of gravity, which is relatively low of course, and then there is an impact factor, because usually not 100% of the speed of the car gets directly transferred to the person, and we can factor that in with that factor, and then we see collision speed with the throwing distance module is 77 for the medium value, which is perfectly in the middle of those two values. So yeah, we have independently double checked our result. Last but not least, we need to export it, taking the medium solution here, saying from the point of view of the vehicle, the pedestrian comes from the, or cyclist comes from the right in that case, and we can click on export. And what we have now is our behavior from collision to final position. And yeah, with that we can directly continue with the pre-collision analysis. Hope you enjoyed today's video and have a great day. Bye bye.